Under pressure. In this module, you will learn what pressure is, how pressure influences volume, why we need to equalize, and what the consequent physiological implications of this are. Pressure and depth. In the previous chapter, you learned that an essential feature of a mask is that it has a nose pocket that can be pinched from the outside. You also learned that a mask with a reduced internal volume can be equalized more easily. These features are directly linked to an extremely important factor for divers. Pressure increases with depth. But what is pressure? In physical terms, pressure is a force exerted on a surface. Let's examine a practical example of pressure. A person walking on fresh snow will sink deep down into it, while someone wearing skis will sink much less. In the two cases, the total weight of the person remains the same, but what does vary is the surface area over which the weight is distributed. Skis increase the surface area, so each single unit of the surface area has to bear a lesser amount of the total weight. There are different units of measurement for pressure. Kilogram per square centimetre, which is equal to the force of 1 kilogram spread over a surface of 1 square centimetre, or PSI, pounds per square inch. Let's now take a look at our planet. All around the Earth, there is a layer of air that goes from the Earth's surface up to a great height. This is our atmosphere. Molecules of air have weight. This means that the Earth's surface and all the objects on it bear the weight of all the molecules above. This force, generated by the weight of the air molecules, is known as atmospheric pressure. At sea level, the sum of the weight of all the air molecules above is equal to 1 atmosphere. Just a little more than 1 kilogram per square centimetre, or 14.7 psia. As we go up a mountain, the column of air above us decreases, and therefore the pressure is less than 1 atmosphere. Now let's go underwater. Molecules of water are much heavier. A column of salt water about 10 meters, 33 feet high, weighs about the same as the entire column of atmospheric air. This means that for every 10 meters, 33 feet of depth, the weight of the salt water generates a pressure of 1 atmosphere. This pressure is known as hydrostatic pressure. As divers, we are interested in the total pressure we are being subjected to. Therefore, we use the term absolute pressure, which is the sum of the hydrostatic and atmospheric pressures. In this way, we take into account both the column of water above us as well as the column of air exerting a force on the Earth's surface. So it's easier to see that on the surface we have a pressure of 1 atm. The final A means that we are referring to absolute pressure. While, as we descend beneath the surface, the pressure increases progressively. At 10 meters, 33 feet of salt water, the pressure is already 2 atm. At 20 meters, 66 feet, it is 3 atm, and so on. It is not easy to notice these variations in pressure because our bodies are made up of mostly solids and liquids, which are not compressible. However, if we take a closed plastic bottle full of air with us under the water, we can see that as we go deeper, the volume of the bottle decreases. Pressure and volume. This means that there is a relationship between pressure and the volume of a gas. In fact, we have seen that the deeper we go, the more the pressure increases and the smaller the volume of the bottle becomes. Therefore, as we descend, the volume of a gas decreases. If we fill a bottle with air under the water and leave the top off, as we bring it up to the surface, we will see the air escaping from the bottle as it expands. Therefore, as we ascend, the volume of gas increases. This relationship between pressure and volume is inversely proportional, meaning that as one factor increases, the other decreases and vice versa. This also means that if the absolute pressure doubles, the volume of a gas halves. If the absolute pressure triples, the volume becomes a third of its original size, and so on. The only parts of the human body that can be affected by these variations in volume are the air spaces. An airspace behaves differently if it is directly connected to the outside and when it is closed. If we take an upside-down glass full of air under the water, as the pressure increases, the volume of air decreases as the water enters the glass. Let's now close the glass with a membrane. As the pressure increases, the membrane will curve inward, intraflexion, equalizing the internal and external pressures as long as the elasticity of the membrane allows this to occur. At a certain point, the membrane cannot stretch any further, and the pressure of the gas inside the glass will be less than the external pressure. This is a squeeze. If the pressure increases further, the overstretched membrane will tear. To prevent pressure imbalance and the eventual rupture of the membrane, it is enough to emit gas into the cavity to equalize the internal pressure with the external one. This is often referred to as equalizing. Being able to equalize air spaces is essential in diving. Equalizing. Before we continue, we have to find out what type of air spaces we have in our bodies. Our lungs are the largest airspace in our bodies, but as scuba divers they are equalized automatically as we breathe in and out. In free divers, who hold their breath underwater, the lung volume is reduced. It is prevented from reducing too much by a spontaneous reaction that increases the flow of blood to the chest area. This phenomenon is known as blood shift. Another airspace, this time artificial, is the cushion of air trapped inside the mask. As the face seal is soft, the volume of this cushion of air decreases as the pressure increases. However, when the mask reaches the point where it can no longer deform, for example because the rigid frame is pushing against the nose, the pressure inside the mask will be less than the external pressure. Such a pressure difference may cause the capillaries in the eyes to break, causing bleeding and making the eyes red. It is very easy to prevent this effect, known as mask squeeze. Just blow a little air out through your nose into the mask as you descend. This is why the nose is enclosed inside the mask. You cannot use swimming goggles for diving. A mask with a reduced internal volume is easier to equalize because you need to exhale a smaller amount of air into it. Another airspace that is connected to the outside by a membrane is the middle ear. Undoubtedly, you will have experienced at least once a strange feeling of pressure in your ears while traveling in a car, an airplane, or diving underwater. What causes this? The ear is made up of three parts. The outer ear is an open space in contact with the outside and therefore subject to changes in the external pressure. The inner ear, where the organs of balance and hearing are located, is made up of liquids and solids. Instead, the middle ear is an airspace separated from the other two parts by membranes. The one dividing the middle and outer ear is known as the eardrum. The middle ear is connected to the mouth by a tube known as the auditory tube or Eustachian tube. As we descend, the pressure increases. If the pressure in the middle ear is not equalized, it behaves in the same way as the glass with a membrane. The eardrum curves inward, causing a sensation of pressure. This difference in pressure causes pain and may even result in the eardrum tearing. The increase in pressure can be equalized by emitting air into the middle ear through the Eustachian tube. By using special equalizing techniques that the instructor will teach you, you will be able to equalize the middle ear and compensate for the increase in external pressure. Pressure imbalances on ascent. Let's now take a look at what happens if the external pressure decreases, as it does, for example, on ascent. The closed cavities, such as the lungs of the free diver, return to their original volume. Open air spaces can eliminate any eventual excess gas without any problems. But what happens to those air spaces enclosed by a membrane? If the excess gas is not eliminated, the membrane will curve outward, extraflexion, due to the force of the internal pressure. This is a case of pressure imbalance in decompression, or reverse block. This situation can also cause damage to the membrane if it is stretched too far. In the case of the middle ear, the opening of the Eustachian tube allows any excess air to escape automatically. In our next module, we will look at what to do if this doesn't happen. Physical fitness and health. Diving is one of the most exciting activities that we can do on our planet, but to be able to enjoy it to the full, you must be in good health, just as you must be when you do any outdoor sports. For example, if you have a bad cold or sinusitis, you shouldn't dive because you are likely to have problems equalizing. Being fit is also important. Strong leg muscles and being fit will undoubtedly help. If you are out of form, get training. The best training for divers is swimming with fins, mask and snorkel, but any other aerobic exercises, jogging, cycling, spinning, etc. are also valid alternatives. If you are out of form, you can easily get cramp in the water, maybe when you are a long way from the shore or the boat. Your instructor will teach you how to deal with this problem. However, if you begin finning again using the same style, it is very probable that the cramp will return. Changing the finning technique will reduce this probability. In the next module, we will examine heat loss and how it can be prevented, look at buoyancy in the water and how it can vary, analyse some physiological aspects of diving and find out what shallow water blackout is. Until the next time.